Fernando, estamos ao vivo, pode dar início, tá?
Ótimo. Ok, bom, então, boa tarde a todas e todos. A gente vai dar início à defesa de mestrado do João Pedro Del Rey. E, bom, eu vou nesse momento mudar para o inglês, dado que um dos membros da banca se sente mais confortável com o inglês. Okay, so we are going then to have the Master Defense of João Pedro Del Rey. And the committee is composed by Professor Dario Rosa from EFT, Unesp, e Daniel Borges, da UF. And also, so I'm Fernando de Mello, I was the advisor of João Pedro, together with Raul Oscar Valejos, who was the co-advisor. João now has about like 45, 50 minutes to present his master thesis work, and then after that we go to the questions by the committee. João, the floor is yours.
Thank you, Professor Fernando de Mello. Everyone can see my screen?
Yeah.
Yeah.
Okay. So I would like to begin by thanking everyone that's watching, and also the committee that have accepted to review my dissertation, and of course the invaluable advisory of my two supervisors, Fernando de Mello and Paulo Vallejo. Now, I'd like to just begin by talking about two different ways of building a castle. And one way is what we call simulation, and the other is learning. And the main difference is how we actually get the final solution, although the final solution is the same, it's a castle. For example, in simulation, some engineer with an architect appears with a blueprint, and we know that we have this kind of standard security rules in engineering, some best practices, and with that we have a set of steps that we need to follow one by one to build this castle. And as we've been building castle for a long time, we know that if we follow all these steps, we will get a reasonable castle, or at least very similar to what we expect. In learning, it's something different. I appear with some pictures of a castle, and you have to find out how to build this castle. And you try to build some prototype, see the difference with the pictures, and from this difference, you try to correct yourself. And I want to note that the main difference is that in simulation, you have somehow complete information or description about how the castle should be built. While in learning, you have this kind of superficial or partial information about the castle, maybe photos of the facade or some stairs, some rooms, and so on. And from that information, we need to build the complete castle. And this is something that we also have in quantum mechanics, because in quantum mechanics, when we want to study some system, we want to solve, want to solve some task. But we also have these two different approaches. In simulation, I give you the description of the system. I give you the unitary, some initial state, or give you some Hamiltonian that generates some evolution. While you're in learning, you have to solve the same kind of task, but with some sort of black box access to that quantum system. And just with the measurements, you need to solve the same task. And these tasks it can be made the same. For example, I can ask for some algorithm that help us to sample from the Born distribution of this quantum system, or find the ground state, or find the expectation value of some observable, and so on. And although the end goal is the same, the way that the information that we have is different. Remember that in simulation, I give you the unitary, the Hamiltonian, something that describes the interaction underlying our system. While in learning, you just have this kind of black box access, just have measurements. And well, we can solve the same kind of tasks, right? what is easier? This is technically our question. We want to infer something about the other method by just using some algorithm or some solution that was obtained using another approach. For example, it would be interesting to see if we can correlate simulation and learning, because when we are rendering quantum computers on cloud, we don't know what is running there. But it would be interesting to affirm something about the simulation, I mean, some about the classical simulation hardness, using just these just measurements. That is all we have when we access these quantum computers at the cloud. And know that given that the results are different, this is our question. Does hard classical simulation imply hard classical learning? And we have some results on the literature that point to some directions to this answer, to this question. And for example, we have this very, we know that pure Clifford circuits are efficient simulatable classically. And we also know that learning the output distribution of these circuits is also easy. When I say easy, I say efficient, and when I say efficient, I say that I want to mean that solving this problem in a classical computer is polynomial on the problem size or the number of measurements that we need to get some error. And so here we have some, let's say, positive answer to that question. I mean, we cannot say that the easy simulation implied easy learning, but we have some match here. We have a system that is easy to simulate and is also easy to learn. But if we add some suitable T-gate, actually, if you build our quantum circuit in such a way, in some specific way, we can prove. This is what this research group here does. They prove that essentially this kind of circuit is very, I mean, it's hard to learn. And when I say hard to learn, it is that this is, if we could learn the distribution of that quantum circuit, we would go against some well-held conjectures in computational complexity. So it's hard in general. We cannot do that, and we don't believe that we will be able to do it. But as we add just one T-gate, we know that this is some constant. I mean, the computational complexity of simulating Clifford circuits is polynomial on the size of the circuit, but it is exponential on the number of T-gates. But here we just add one T-gate, and so it's just some constant overhead on the polynomial complexity, and so it's also efficient. So this is some, let's say, a positive answer, some negative answer to that question. We also have some other examples. For example, we know that if we add noise in general, we can make simulation easier. This is the way that we can simulate that those quantum advantage claims, because while real quantum computers have noise, because they need to be implemented in the real world. And also we have large research body in quantum mechanics that try to use learning methods that shows that if we add noise to our distribution, to our problem, the neural networks or the problems in general, they converge easily. I mean, not easily, but easier than if we are consider a pure state. And also we have another a positive, another negative example. We know that multi-gate circuits are simulatable under certain locality conditions, but also learning the distribution of that that kind of circuits is NP-hard. And this is again another conjecture that we think that we want to be able to surpass. And so that given that we have examples about some systems that has equivalence, a kind of equivalence on the hardness, how can we develop some way to, given a system, find if we have this correlation or not? Well, for that we propose some framework. First, it is an experimental framework. So we need to find some consistent that has a kind of parameterized simulation complexity. And then, of course, we need to give this system and solve it with learning algorithm. And we need to measure how hard it was. For the first step, we can use, for example, the class of quantum Clifford circuits. We know that it is efficient to simulate, as I said. But to every new T-gate, we add an exponential overhead. And so we can think that the number of T-gates is some knob that increases the computational capabilities of our system. Or another example, we can use matrix product states with a given bond dimension chi. These matrix product states are systems that are used as an answer for 1G systems that have limited entanglement. And the bound on the entanglement is controlled by this parameter chi. In general, the contraction algorithm also scales with this bond dimension. And so if you change the bond dimension, we add the more entanglement and we get a harder system to simulate. And also, of course, we need some metric of complexity, of learning complexity. And in general, it can be, for example, the space complexity. We can think about the number of parameters in our model, or the number of steps to this model get to the right answer. This is the time complex, or the number of samples, which is the statistical complexity. And with these two ingredients, we can build some kind of graph that has two different. We have two different possibilities. Essentially, one in the x-axis we have the simulation complexity. In the y-axis we have the learning complexity metric. And essentially, we can see some correlation. I mean, if we can increase the entanglement, we see that our model, so our problem get harder and harder for our learning model. Or we can see something like this right graph here, where we cannot pinpoint any kind of pattern. And this is something inconclusive because, I mean, in both cases is not general. But the most that we can do is that we solve or not solve some correlation between the simulation complexity and the learning complexity for that system. Now going into the method section. Remember that this is somewhat experimental, and this is let's say the complete protocol. First, we need to select to find some quantum system with some complexity parameter phi. And remember that, as I said, we use the matrix product states that we just call MPS, number one. And we use MPS, whose complex parameter is the bond dimension, and pure Clifford circuits, whose complex parameter is the number of T-gates. We need to generate some quant state from this class of states, and we perform some measurements on some bases, and you generate a data set, and with this data set, we give it to some learning algorithm. And now going to the first part, which is the data set, we have two different data sets and we aim to measure two different things of two different kind of quantum resources, let's say. In MPS, as I said, the idea is to see how our learning metrics correlates or changes with with entanglement. I mean, if we generate systems with larger and larger bond dimensions, we can see in this page curve-like graph that we get higher entanglements. So here the axis, the control source is entanglement. While here on the right for the random Clifford circuits plus the gate, the idea is not to vary the entanglement. The idea is to vary the computational capabilities of our system, because we know that pure quantum, pure Clifford circuits are not universal. I mean, when say universal, they don't have universal computational capabilities. And as we add each port outside the set of Clifford gates, and generally just shows the T gate, we get universal computational capabilities. As we add more and more T gates, we can, let's say, enhance our capability of representing a unitary over the qubits in that circuit. And note here, this is the same graph on that I showed before. And remember that the idea is just to change to increase the quantity of magic or non-stabilizers. And so for that, we increase the depth of the circuit until we got some very saturated page curve for our system. So the idea here is to saturate entanglement and just vary the quantity of magic or non-stabilizers. And now that we have our systems, we need to employ some learning algorithm. And for that, we use neural networks. And neural networks have some kind of recipe. And in general, we need to first fix some architecture. That is the way that the weights on our model will combine to get the final answer. And this is we need to show which kind of correlations our model can learn or not. And then we fix some loss function, and this loss function is essentially what measures how wrong the model is to the right solution. And we, of course, need to update the parameters in our model, the weights. And for that, we use an optimization algorithm that in general is just the gradient descent. And we chose to use these last two steps as a way to implement our learning difficulty metrics. We use the geometry of the loss landscape, and because we know that the curvature of the Hessian of that loss function is correlated with the generalization capabilities in our model. And also we chose to impose some training restrictions on the optimization algorithm. And the idea here is that by imposing these training restrictions, we can get a better, we can get a smoother variation in the final accuracy. We can, let's say that with a fixed capability, the more we can see better without variation, how the model responds to harder and harder problems. Now going to this last one first. This is the random subspace optimization method that I will just call RCO. And the RCO is the way that we chose to limit the capability of our model during the training algorithm. And this is very interesting because it came out in a paper that asks some very interesting question. For example, we know that MNIST, we expect that MNIST, solving MNIST is easier than learning how to play Atari. And solving MNIST is the problem of classifying handwritten digits from 0 to 9, of course. And we expect that, well, it's easier to identify digits than taught some machine how to play video games. But now it's not so easy to claim that, or so clear to say that classifying 1,000 different objects in natural image is easier than playing video games. When I say classifying objects, I say about phones, people, cars, etc. And for that, they defined this RCO method that works during the training algorithm. And here, just to exemplify, remember, the main idea is to not let the model walks around the parameter space freely. The idea is to just let it update the weights on some given subspace. And here in this 2D problem, we have the contours line of some quadratic function. Here is the initial state. And if we would use unrestricted gradient descent, we would just step on the direction on the minimum. There's something here. But now that we generated this random subspace before beginning the problem, we see now the model can just walk on this line here, which is the chosen 1G subspace. And this 1G subspace will be controlled, will be defined by this random matrix that we generate before beginning the training. So this is our first learning metric. Remember that this is not the learning metric. What we actually use is just the final distance between the quantum generated distribution and the learned distribution. And this is just a way to really fix how powerful the model is. Now, the second kind of metric is based on the laws, on the geometry of the neural network's loss landscape. And here we have some interesting images from this paper that defines, that develops a way to visualize high-dimensional spaces on, I mean, we have to see it in 3D. And this is the loss landscape of the same model, but the difference is that when I say same model, I say the same size, the same kind of interactions, and so on. But here we use some trick to make the loss landscape smoother. And they verified that this model here on the right, with these tricks and with a smoother landscape, generalize better. And what is generalization? Why we can think, why we can use the generalization of this idea here? Generalization is just the property or the capability that neural networks have to perform well on data that wasn't present on its dataset, on its training dataset. And we can think that if a model is capable of generalizing well, it means that it learned some underlying structures, or found some low dimensional manifold where data live is. And so it could, as it learned the problem well, it could perform better on data that wasn't in the trained data set. Essentially, we can think that the model isn't simply feeding data, it's learning how that data is generated and so on. And we also have some different results. But remember that the main idea of the hashing is, we can look at this equation here. If we expand the loss function on the neighborhood of some parameter theta, and if this is if this is some local minimum, the gradient is almost zero, and we see that the variation is controlled by the Hessian, and so it depends on the Hessian norm, and so it depends on the spectrum. And we have a lot of interesting results that correlate the Hessian spectrum with the Hessian spectrum controls the curvature, and we can correlate the Hessian spectrum with the problem complexity, let's say. For example, this paper is interesting. They reproduce it with a lot of different data sets. And cipher 10 is the problem of identifying 10 different objects in natural images. And we found out that the spectrum of the Hessian is divided in two parts. One, you have some kind of dense bulk around zero. And now you have a set of outliers that are simply some kind of discrete points in the spectrum. And they realized that the number of these outliers is very similar to the number of class. And we can think that, well, the spectrum shows some traits of complexity, because if we have more class, we have more outliers, and we can, if you have more classes, the problem is more complicated. We also have this other result that I use, because I used only the maximum eigenvalue, is in general just called the sharpness on the neural network literature. And the maximum eigenvalue also shows some traits of the problem complexity. Here, they did some simple experiments. You have you have two classes controlled by these Gaussian clusters, and this is a simple classification problem. And we can think that as we decrease the size, the distance between these two clusters, we get a more hard problem. We get a harder problem. And they found that as they decrease the distance, we are dealing with less separable data, and so the model need to let's say to draw some more complicated decision boundary between the classes. They realized that as we decrease the distance, the eigenvalues, the maximum eigenvalue also increases. And putting together this and another of results, I chose to use just the maximum eigenvalue. And also because it is simpler to just compute the maximum eigenvalue using the power method than diagonalize some big matrix. Now, just to review our methodology, we begin by finding some complex parameter phi, which is, as I said, the bond dimension for MPS over the number of T gates on a pure Clifford circuit. And this parameter has the condition that it should controls or not modulate the simulation complexity in our system. We generate some quantum state from there. We sample some measurements on that quantum state. We give this data set for a learning algorithm. And after the model trained, we employ some learning difficulty metric that, as I defined, is the one based on the curvature, and other is the usual learning metrics, distance between the distributions, but in a restricted scenario. Now, going to the result sections. First, let's begin with the matrix plot states using our RCO-based method. Remember that the idea is just to restrict the power of that system, of that learning algorithm. And here we increase the dimension, and we can see that indeed we see a corresponding increase on the error that's given by the total variance, the distance between the distributions in the end of the training. And so we could say that, well, our neural network is actually seeing the problem as harder and harder as we add more entanglement, as we add more correlation, or maybe we can say quantum resource to that system. But here we can see that we have some, let's say, weird behavior here. We have some kind of saturation. And I say weird because we don't expect that. We are essentially saying that our model at some point cannot, we would expect some kind of monotonic increase of the hardness of that problem, and not this kind of saturation. But note that this saturation occurs just for this top curve here. And note that this is also the curve with the smallest subspace dimension. And essentially, the idea is that the model cannot remember that the subspace dimension is essentially the quantity of different parameters that we can actually change in our system. And so we are trying to modulate, I mean, to fit some probability distribution on thousands of outputs using just 25 parameters. And this is somehow more very complicated. If we change in one direction, we need to also change a lot of different outputs. And due to that, we came to a point where we cannot decrease the loss, and any change would increase the loss function. And we can see, due to this example here, this is exactly the same kind of graph from the same kind of neural network, training procedure, and so on, to this blue curve here. We can see that when we have a very limited system, essentially it just gets the unitary, it's the uniform distribution of the bit strings. It doesn't matter if we have some kind of easy problem or a harder one. The model just keeps outputting the uniform distribution. And the idea is that we have 1,000 different events, and we can just change 25 parameters to fit this distribution. And so we cannot change the probability mass in one area without affecting other area in such a way that we would decrease the loss function. And so this is something that points out the fact that we need to use some minimum subspace dimension to get meaningful results. Now, I decided to do some kind of sanity check because, as I said, we have this increasing with more entanglement, and so it's a good result. It's what we were expecting to see, but that the previous graph was obtained using, let's say, a fixed number of training steps. And here I chose to just let the models train more and more how many times they wanted. Of course, we need to stop at some point, and I stopped after 5 iterations throughout the entire data set without any improvement on the loss, on the accuracy. I mean, the total variance distance. And we can see that we get essentially the same kind of results for some neural networks. We see that we have this kind of increasing as we add more entanglement. We also have this saturation that I already discussed, but now we see some kind of large error bars here, some outlier behavior that is weird because it's essentially saying that the model solve the problem as easier as we add more entanglement. And why is that? We can see here on this right graph the quantity of steps that each model used to get to the finals, I mean, into convergence. And we see that as we increased the subspace dimension, as we give more freedom to walk around in the parameter space, the model uses this freedom to walk more, explore more, and find better solutions. But with very, let's say, lobotomized neural networks, this isn't the case. Essentially, the model as it cannot fit any complex distribution. It just iterates through the data set until some reasonable looking solution that, as shown, as it is, as I showed, it is uniform like distribution. And due to that, the model is very dependent on the initial conditions. And so it will get some good or bad solutions depending essentially on luck. And so putting together this result, this kind of sanity check, and this the fact that the model somehow needs some minimum dimension, subspace dimension, we can say that this method to work has some condition, and this condition is that we need to imply to show some minimum threshold, some minimum subspace dimension. Now, going to our curvature results, we see here that this is the same system, but we are increasing the bond dimensions, the segment, and now seeing how the curvature computed at the training end is related with ensemble. And we see that indeed, as we increase ensemble, we get more and more complicated loss landscape, or we can say more curved loss landscapes. And remember that, as I said, this metric is interesting because the model it is some prior, some intuition about some way to find if the model learned or not the intrinsic relationship between data points. And so we can just say that as we add more and more entanglement, the problem gets harder and harder for neural network. Just one observation: this graph was constructed with the same kind of neural network, the same kind of training procedure, and the only difference is the final step. I mean, sorry, the final. The only difference between the runs was the data set. We can say that, of course, this difference on the end of the convergence in the curvature is just due to more entanglement. Now, going to our second system, which is the pure Clifford circuit with the addition of some T-gates. We have here the graph with the Hessian sharpness, the maximum eigenvalue, as a function of course, the number of T-gates. And we see that indeed we have the kind of result that we would expect. As we add more and more T-gates, the system is getting harder and harder to learn. And when they learn is to find some inner structure, as I already discussed. But we can see two different behaviors here. We have some kind of saturation. And this saturation, we have some hypotheses. We didn't done any kind of simulation to test it, but this is some intuition. We saw that the curvature is affected by entanglement, right? But by construction, these Clifford plus T circuits are circuits with, let's say, constant and saturated entanglement. But this entanglement is an entanglement that use the Hessian, that use the entanglement entropy along the chain. We essentially find some cut, and you compute the von Neumann entropy on that traced out density matrix. And so what I'm trying to say is that we have different metrics of entanglement, we have different kinds of entanglements, we have different ways to spread correlation and entanglement information in our system. And we also know that we see somehow a kind of transition when we add T-gates into a pure Clifford circuit. We see a change on the entanglement spectra of our system. Pure Clifford circuits have a kind of entanglement spectra, the Poisson distribution, which is related with integrable systems, systems that are simple, systems that aren't chaotic, systems that doesn't thermalize. While if we add even just one T-gate, we see a transition for Wagner-Dyson distribution. That is a kind of distribution that is correlated with chaotic systems with universal computational capabilities, systems that are not integrable, that thermalize, that are complicated to solve in general. So as the entanglement spectrum changes, we can expect that the distribution of entanglement and the spread of information also changes as we add more T-gates. And this is something that we need to do more simulations, more experiments to test some kind of noisy behavior here, and I want to discuss it about think about this noise behavior and maybe some weakness of our methods. Because, for example, in this system here we have the Clifford some sample distributions. On the first row we have for just one T-gate. The second we have just for two, or I mean for 20 T-gates. And we can see that these distributions are somewhat different. And when I say different, I really say in some hand waving way, because I didn't employ any kind of metric to measure that. But note that the loss function is some average of our neural network computed over these strings here. These probability events. And but technically the model, even for the model, we know that the labels on the event, the index doesn't matter. But so we see that the model essentially he see two things. There are some examples with this constant height and others with zero. And then another sample, we see some distribution that is essentially uniform, that has just some one level. And here again we have another very different distribution with respect to the heights that has essentially two heights. But as we add more and more gates, if we think about the difference on heights, we see somehow some very similar distribution. And I'm talking about that because it can explain why we get lower error bars on the end as we add more and more gates, and high and large error bars in the beginning. And this, as I said, is some weakness because I'm showing that this curvature is somehow very dependent on the probability distribution, or the input, on the format of the input distribution. And now, on the last result is somewhat a known result. We have here the graph of the total variance for different restricted models trained on Clifford circuits with increasing number of T-gates. We see that essentially we cannot affirm, we cannot say anything about the system, we cannot find any pattern, any clear pattern. We have some erratic behavior where better, more restricted models perform better than less restricted models, but we see some kind of saturation and this large error bars here that, as I discussed, it can be a hint that we need more and more. We need a larger subspace dimension to see something meaningful. Now, we have two options here. First, actually we cannot find any correlation between the number of T-gates and our total variance in this restricted scenario. And we call it a N-1. This is some experimental work, and we are trying to find relationships for a given system, and we could just say that, well, we didn't find any such a relationship, and it's okay. But the other option is, as I said, we maybe just need to increase more and more the subspace dimension, because if first we saw that this metric is somehow very sensible to the increase of entanglement, and here we have some system with saturated entanglement. Although, of course, I discussed that this kind of term changes. We have a system with saturated entanglement. And this metric measures that. And maybe we need a very large subspace size to see the difference. We have to first go beyond the first letter, that is the problem of entanglement, and then from this point learn how the magic can change our total variance distance. And this, as I said, is very reasonable because this kind of behavior here was found in in the case of in the MPS system. And I argued that it's due to limited subspace size. Now to close the presentation, remember that our initial question was about the relationship between two different ways of finding solutions for a given, let's say, quantum problem. They are different just on the way that we can get to the solution. One is simulation, the other is learning, and one I give you some description of the system, the other I just give samples, and it would be interesting if you can find some relationship between them. For that, we employed a kind of experimental setup where we fixed two different quantum systems, MPS systems and Clifford cluster circuits, where in each one we chose some parameter that increased the simulation complexity, and then we measured the corresponding learning complexity after we trained some learning algorithm. And we saw that for the MPS system, whose complexity is modulated by the entanglement, we saw very good, a very clear relationship between entanglement and our learning metrics. And so we can say that simulation and learning complexity are correlated for that kind of system and the chosen learning metrics. While for the Clifford plus T circuits, we got some, let's say, mixed results. First, we saw a clear pattern when we considered the curvature-based metric, and we saw that essentially as we increased the thing count, we increased the curvature, making the problem less generalizable, let's say. But we didn't see any kind of trend when we use the RCO-based metric. And as I discussed, this is we have two options. First, this is something that is similar to what we saw in the literature. We have systems and resources that that have this correlation and others not. Or this is just some problem about our method that, as I showed, we need a minimum subspace size to get meaningful results. And from now on, I will first try to do more experiments to get to verify if really that saturation is due to some kind of change on the entanglement spectra, and we need to think more about how we can do this kind of experiments. Also, we need to scale to use larger and larger G. This is a little more complicated because we need to employ different methods to generate that random matrix, which is very large and in general cannot fit easily in a GPU. And of course, extending from this work, we aim to use different generative models. We can use VAs that are variational autoencoders, or diffusion models, or normalized flows, or generative adversarial networks. And we can use these different models in different measurement bases. I mean, doing something like a conditional generation where before sampling measurements, we teach the system how the distribution behaves for different observers. Of course, we can employ different metrics. Just by increasing the number of different generative models, we get we get the opportunity to use different metrics. And also we can, of course, test different systems with different complex parameters. We can, and of course, we can employ this kind of metrics beyond our fundamental question. I say it here because our question is something very fundamental. It's just the relationship between two paradigms about how to solve some problem. How to solve some problem. And now our question is about the relationship. But note that the chosen metrics are based on the neural networks, and we are seeing on the literature the usage of neural networks for a lot of different problems, even for simulation problems. And we can think that, well, if the problem is harder to solve for that architecture, maybe this is not a good architecture to solve that problem. And so we can use these learning metrics as a way to search for better architectures for different problems, even for simulation problems. And with that, I finish my presentation. I would like to thank everyone that watched. And we pass, of course, open to questions. We pass the floor for Professor Fernando de Mello.
Thanks a lot, João. Perfect timing, 50 minutes, like sharp. Okay, so once more, I'd like to thank the committee, Daniel and Dario. You got claps already.
Yes.
Okay, so now we pass to the oral examination part of the defense. And as tradition mandates, so we start with the person which is furthest away. And that's clearly Dario in this case, although Niterói is really far, but not that far, right? São Paulo is way further away. So Dario, thank you a lot for being part of this committee. We are glad to have you here and want to hear comments and suggestions and questions. So please.
Yeah, I mean, essentially, I have two comments that are more, let's say, more like clarifications and discussion more than precise comments on the thesis per se. So the first one, you said that this statement that, let's say, having a Clifford circuit plus one single T gate already drive the system toward Wigner Dyson and so on. This is, let's say, a statement that is around. However, I mean, I cannot say that I know very well the literature, but I remember I had by now a few years ago a talk by Alyosha Am where they published this paper that is called, it has a very funny title, Quantum Chaos is Quantum, in which essentially they argue that to have really a transition to quantum chaos, I don't remember exactly how they determine that, probably via the OTOCs, I think. I think they don't use the level statistics, they argue this via the OTOCs. And I think they argue that the T gate, the number of T gates that you need in order to really have a chaotic system should scale with n, the number of qubits. So let's say one, it's enough to induce, let's say, the level correlations transition, while apparently to have a more complete properties of quantum chaos, whatever it is, unfortunately right now I don't remember which metric they use, they need, let's say, more. They need, an order n number of T gates. So based on that, I was wondering if probably in the second or third of your slides, you point towards this tension between, let's say, simulation and learning, saying, with just one T gate, you still simulate well, but you don't. So I was wondering if perhaps simulation is more affected by level statistics, while learnability somehow is more learning via the OTOC. And so, or the other way around, sorry, probably simulation is more affected by the OTOC and learnability is more affected by the level statistics. So maybe this discrepancy between the two can be related to that. This I don't know. It's just, I don't know, maybe a suggestion or whatever. I mean, if you want to comment, of course.
Yes, I think I don't remember what I said, but we have some works. For example, this single T gate do something, some transition about the integument spectrum, but for some kind of conjecture about the learnability of systems. And the idea is that if you have some chaotic system, it's get harder and harder to learn that from some measurements, because essentially we see correlation. And this system is yet easy to simulate. And
Yeah.
about this work that you said, quantum is quantum, I didn't read it, but it's on the list, let's say. And there's another work that I actually used. I don't remember if I cited it in the dissertation. I think that I didn't cite.
Mhm.
This work uses also just correlation. It doesn't measure standing spectra or anything about that, but it computes how the information, how correlation is spread in a system as we add more and more gates. And they found out that correlation is spread faster from something like logarithmic on the system size to something linear as we add more and more gates. And they
Do
found
you
that
remember?
this,
Do you remember if the transition between the two is of order the number of qubits or something like that? Because that would be probably in agreement
yes,
with
it's on the order of qubits. It's because of that,
Eh,
it's
okay,
2n, two
okay,
times the number of qubits. And because of that, I just in the beginning just simulate into 20
okay.
gates.
So that could be in agreement with Alyosha's statement, cioè that even though level correlation, apparently, I will say probably the message of this is that level correlations are very sensitive to just one or two T gates, while instead dynamics require more. And so maybe simulation and learning are, let's say, one related to level correlation, the other with dynamics, something like that. I mean, this is something that came to my mind. Then
Mhm.
another very, let's say, general question, as you emphasized many times during your presentation, what you did is essentially an experimental work at the very end. Is there any tool on the market that could be used to make these statements, let's say, no, we lost somebody? No. Is there any tools on the market that could be used for, let's say, more formal statements?
I didn't investigate this direction,
Mhm,
so I will say that essentially I don't know.
mhm,
Although I have seen some results that studies the learnability. I mean, there's some interesting papers that talk about some kind of learnability in, in of sort phase transition on learnability.
mhm,
But in general, they just put some formal problem and try to solve not with neural networks. They try to solve with, for example, something that has more more known properties like linear regression
mhm,
and using samples that come from classical shadows that we have some good bounds. So I have seen people doing this kind of thing.
mhm,
But the idea, the main idea was to use neural networks because essentially you can get it's a kind of black box model, although we can interpret it using the right the right tools. But the idea is just to give some distribution
mhm,
without knowing anything about the system, about the device, and let it train and see the final metric. And for example, it would be interesting if we could see that as we add more gates, some neural network metric increases as we because we are increasing the computational capabilities of system. And just the samples is just what we have.
mhm. Yeah. Then okay, I don't know. I keep shooting with the questions, or maybe we alternate. Then okay, I keep going.
Yeah, keep going. I
So
mean, as much as you want.
okay, another that
But
came
of
to
course,
my
Daniel
mind.
can, I mean, if you allow, Daniel can
Yeah,
jump in if he wants to.
yeah. Another that came to my mind, perhaps another difference that could make the comparison between T gates and MPS harder to make, and could maybe explain why, let's say, with MPS you have a very clear, I don't know, trend. I mean, you could say many things while the other was. It's because I would say, at least in your architecture, when you introduce these T gates, how can I say? I mean, I don't know well how to formulate, but let's say in MPS, you add more and more entanglement, but you add in a way that somehow keep a notion of locality. Let's say adding the bond dimension, you make the correlations a bit more long range, but somehow the system keeps a sort of no locality. Instead, since you add the T gates in a totally random fashion, I would say from step zero, your model become immediately highly non-local. I don't know exactly in which sense I can formulate this statement, but I have this feeling that you somehow destroy locality at the very first step. So, do you have an idea how you can check if locality is playing a role in this game, or have you thought about that? Or
First, I have a question. This is
Mm.
a question. We can say that if I put the position in space that I put the T gate changes something. I think that yes, because from that point onwards, we have now magic, let's say.
Indeed.
And so I could think that, for example, I could fix some position or T
Mhm.
gate, and then this is something naively. I want to say that maybe there is a way to fix the locality, and we measure that by just using correlation between spins.
Mhm.
I don't know,
Mhm.
as a function of distance, and just generate random circuits with a T gate at some point and apply the measure there. I mean, train the neural network and do
Yeah.
everything there. I just don't know if we can, let's say, fix this locality. I think
Yeah.
that
Yeah. I
maybe
don't know either.
varying the position of one T gate, we can get something similar, something that okay, it shows some kind of locality profile, but I don't know if it's possible. Maybe you
Yeah.
can do something very naively, that is where you sample some quant circuit, do the same kind of experiments, but also measure the locality profile. I mean,
Mhm.
the correlations. And from that, we do a lot of different experiments and try to plot it in the end.
Yeah, yeah. Again, I absolutely don't have right now an idea of how one could run such an experiment, but yeah, it's probably a feature that would be worth in some way to try to.
May I comment on that?
Please.
Yeah, I mean, I guess we have to have in mind that the Clifford circuits, they do generate loads of entanglement, right? So, I mean, it's going to be non-local to some extent, even
Mhm.
without T gates. So these will be very hard to, I mean, I don't even know what it means, right? And to some extent, because if you're looking correlations of far apart wires in a circuit, you would get them even without any T gates, I'd say, right?
Mm.
Because you
So
are looking at very deep circuits, right? So
exactly, yeah.
there's no kind of
Ah,
notion.
okay,
Yeah,
okay. So, okay, yeah. So since they are deep, you say in any
yeah.
case you are also in the. Okay, okay. I see.
Yeah, we are generating entanglement, even kind of GHZ type of entanglement, let's say.
Okay, okay. So in that case, probably no. My point doesn't apply in the sense that the MPS ansatz is already. Yeah. Okay. Good.
Although, I mean,
I
there,
mean,
there might be something there in terms of like where the T gates are positioned relative to each other, right? So if the first T gate and then the second one are kind of close to each other or far apart, maybe that there you might get a little bit of kind of a difference in terms of locality.
Mm.
I know.
Yeah. Okay.
I think that we
Fine.
need
could be.
to fix some way, fix some way to measure this locality.
Hmm.
Because I mean, this is not my area, but I see some papers that say that well, if you have this transition to Wigner Dyson, we have less locality in your state, you get more scrambled information. But we see this behavior on Clifford plus T, and maybe we can indeed measure that some
Hmm.
way. Maybe there is some magic to.
Yeah. Again, I don't remember Alyosha how exactly. I think that maybe can help in distinguishing what do they mean by quantum chaos is quantum. So there should be also something related to that. Okay, finally, I have, let's say, a speculative question. I mean, coming back to your your very first example about the castle. So, do you think that, so suppose that you make a model that learn extremely well, so can, let's say, reproduce perfectly the result of the castle and so on. Now, can you use that? I don't know if, again, I'm not sure it's well posed the question, but can you use that to ask the algorithm a new simulation strategy. So can you, let's say, can you use this learning ability to make a better simulation? It's like you make a better, how can I say, set of rules to mount the castle out. This is a general question to people that work in neural networks. I think it would be really great if once the neural network have learned something, would be super great if you can ask what the neural network have effectively learned. You could use that to learn something that you still don't know.
Yes, I think that this is trending right now on the area of deep learning. Is about interpreting what the neural network have learned. And we have some very interesting results. I don't know if I can find it here. Well, but essentially, what you're saying is that well, the learn if it went so well, it actually learned some best way to do that.
Yeah.
And we have this result, this is grokking, so-called grokking. You have heard about that?
Can you repeat it?
Grokking is from some fiction literature where aliens have some kind of different learning method. Then when you learn something so well, you somehow mix grokking. Yes, you fix you mix this knowledge with your soul, and people use this grokking term. And what is the problem? They give a data set with modular addition to a neural network. And of course, you have you give 1 plus 2, 1 plus 3, but then in the data set you don't have n and 5, for example. This is just on the validation data set. And at first, the neural network just memorized the entire data set, train data set, and so it gets 100 accuracy on the training data set, but 0 accuracy on the validation data set. But then at some point, if you just let train more and more, we see some kind of phase transition that indeed there are physicists that are modeling this kind of thing as a real formal phase transition, where the the accuracy on the data set, on the validation data set is maximum. Like it really learn how to make modular addition. And now the researchers did some kind of investigation, and they found that the neural network learned really some algorithm to make modular addition. They found representations about Fourier series, discrete Fourier series inside the layers, and they could track it from the initial layers to the final answer. So I think that yes, we can do that, and people are trying to do that.
Great. Okay, I think I'm over for the moment, at least for the moment, let's say.
Thanks a lot, Dario.
Thank you.
Thank you for the great questions and discussion. Okay, with that, then I pass to Daniel Borges, Professor at Federal University Fluminense Federal University. I'm not sure how the order goes. Commutes, I suppose. Thanks a lot, Daniel, for reading, and we are eager to see your comments.
Okay, thanks. Thanks, João and Fernando and Raul for the invitation. Yeah, so I have a bunch of notes written down here on your PDF, and I won't go through everything. I'll send you the annotated PDF later. I just want to kind of stop by some highlights. But I want to start off by saying that I liked your dissertation a lot. The first chapter, I think the one with the thing with the castles, with the kind of little story, I think that's really good. I think we kind of get in the habit of thinking that you should write everything super seriously, and then everything gets kind of equally boring. And I I feel like it would require some amount of editing still. I think like it's not that clear what the point is, but I think like it's an extremely good initiative. Kind of try to have like good humor in your writing in general.
But
So I think
now
that
I
was very
have to
good.
write an epilogue.
Huh?
Oh, sorry.
Right.
Now I have to write some epilogue.
Right. Yeah. Yeah, no, I mean, I think like I really enjoyed seeing that there. So like in general about the dissertation and the sort of I do have like a few technical comments slash questions. The first thing, there's one thing you repeat every so often through the dissertation that I don't agree with. And I think it kind of it shaped the motivation that you're describing for your work. And in a way that I feel like I know I don't agree with it in general. So just to kind of grab one snapshot from what you wrote. There's a point in the chapter 1 where you say, oh, you're talking about entanglement, and you say, oh, entanglement is not sufficient for quantum computing because, you know, you have like very entangled states that are classically simulable because of, you know, kind of Gottesman and so on. And then you say, oh, now we have a resource theory of magic, you know, which presumably is the ingredient that leads to universality. And you say that a lot, right? I mean, every so often you say, oh, you know, we studied entanglement, but entanglement doesn't tell us anything about universality. Magic does, right? And I think that distinction is, personally, I think that that's kind of pointless because, you know, I can construct a state that has a lot of magic and it's also classically simulatable because there's no entanglement, right? If there's no entanglement, it's also classically simulated. So it's very clear that, you know, they're both ingredients that you need. Like, I think that the general approach of trying to find one kind of magic dust, like magic powder, that's the one thing that makes quantum computers click. I think that that's doomed. I think like people maybe try that early on in the beginning and maybe they thought it was entanglement. But I mean, I think we've learned over the last decades that trying to pin down one ingredient is not a good not a good strategy. There's no single ingredient. And the way that you write that sometimes suggests that you're looking like you're putting more emphasis on that, and I think it's kind of warranted, right? So I think like, you know, and there's even a chance that, you know, there's an interplay between these two things, right? So if you have like too much entanglement, you sometimes also expect, you know, even if magic or whatever, right? If you have like everyone's perfectly, like everyone's maximally entanglement with everyone, and you measure one qubit and then everything collapses, and now you don't have any quantum computation again, right? So like it's not like quantum computing is not kind of monotonic in these things in an independent way, right? So you totally expect, like, there's even some papers talking about that, like non-local magic recently, right? In terms of magic that's only useful when the state is entangled or only appears for entangled states. So it really is like an interplay between all of these ingredients. And I'm not sure I agree. So like, for instance, they were saying before about you know, oh, what about this locality with the T gates, right? So you have Clifford and then you kind of saturate entanglement. And then you start putting some like random T gates everywhere, right? That's not obviously the best way to do quantum computing, right? I don't know if the best kind of, the more complex quantum computing algorithms look like that, where the kind of magic is just kind of randomly splattered onto the circuit, or whether, you know, there is some better way where you kind of place the T gates in well-defined locations in a way that does correlate with entanglement. So I would be just kind of cautious in trying to ascribe too much meaning to that. And also of kind of thinking that what you did is probing both resources independently. That's not obvious, right? So when you say something like, oh, you know, this is a way to isolate the effects of magic because I saturated entanglement, it's not obvious that that follows, right? Because it could be that the effects of magic are different depending on how much entanglement you have. So I would kind of, I don't know if, you know, to what extent you're going to revise this and kind of rewrite some of these bits. You don't have to. But just like for the future, you know, like I think that I'm not sure that there's a lot of like the work is very nice, right? I think that what you did is very nice in general. I like it a lot. I just don't think that, you know, maybe the sort of this motivation is the better motivation for doing it. Because I think like people have kind of given up on trying to kind of be too precise about which ingredient. And then you can get things like match gates, right? Which has a lot of entanglement and a lot of magic and are still classically simulated. So I would kind of, you know, tone down a little bit, I guess, this sort of taking the resources themselves too seriously. So that is one thing that I've got the feeling kind of throughout the entire dissertation. I think I would be careful. Okay, that's one thing I had to mention. The other thing about the dissertation that I feel like you talk about stabilizer states a lot. You don't really use the formalism of stabilizer states, right? Because, the point is the fact that Clifford circuits are classically simulatable, you don't care about that in a sense, right? Because you're not simulating them. So you never need to learn like about the stabilizer formalism in order to do what you did. At the same time, you use a lot of jargon that comes from that. And I feel like a reader might get confused or not follow. So, for instance, in the introduction, there's a sentence that says, it was proved that a state is inside the stabilizer polytope if and only if it has non-negative Wigner function. And like half the words in that sentence you didn't define. So unless the person is already very familiar with all of that, that sentence doesn't mean anything, right? So I feel like, and again, it's not super like understanding stabilizer formalism is not super important to understand what you do. But I kind of feel like you could have added something, a bit more detail about stabilizer formalism in the dissertation, just so that you do it with MPS, right? So I kind of feel like there should be kind of a one page of just what are stabilizer states, and why are they classically simulated, just so the reader can. What is the stabilizer polytope? Why do you talk about it so much? Again, like you don't use it for your results, so the person doesn't really have to understand it. But for instance, there's a plot you show where you're talking about when t equals 0, and then you show like the probability distribution, right? And there's a bunch of things that only have 2 different values or a bunch of different values. That's a very well-known thing from stabilizer theory, right? You know that inner products between stabilizer states are always powers of 1, like always multiples of 1 over 2 to the n, or whatever. I don't know. There's some 1 over the dimension of the Hilbert space, something like that. Right? So you know that the probabilities could not have much different values than just those. So you could have expected the graph to look like that, just from stabilizer theory. And if you told the reader that, the reader might kind of get a better intuition of why the graph looks like that, right? And not just like, oh, what a random thing that the graph just looks like this big chunk of red. So I think like telling the reader a little bit about the stabilizer formalism could be useful. And then saying, like this isn't actually useful in practice because we just sample the Clifford circuit in this way and then just simulate that. So we don't actually use stabilizer formalism. But, it still gives kind of some intuition of why things behave like that.
Yeah.
So that's another thing I think would be important. Sorry?
Oh, you can. Well,
Okay. Let's see what other important things I want to say. Right. Yeah. There's the other thing. So for instance, when you have this sentence, right, where you say, the 2 systems here, the 2 systems used here offer both. You say, matrix product states can be viewed as proxy for quantum computers of bounded depth, while T-doped quantum circuits offer a glance into the effect of universal quantum computation on learnability. But again, both models become universal for quantum computation if you tweak the parameters enough, right? So it's not like the MPS thing is not. Yeah. Okay. There's some minor comments here that I'll send you later. Let me see what else.
in general,
Okay.
I agree. Sorry.
No, go
No,
ahead.
in general, I agree because I think something about the phrasing, and as you said, it's a little strong to say something that the magic or non-stabilizer is the last ingredient. Okay, I agree that this is a little strong, but we have this. It's complicated to separate these 2 metrics, as you said, and the idea was just to add. I mean, even MPS has magic.
Yeah.
Random MPS has magic, so I technically didn't separate them. But the problem is, as you said, you cannot separate this, and so it's a little complicated. And I don't have any idea about how to do that actually.
No, sure, but then you can like precisely
I
because
can
of that,
rephrase.
you can be kind of
Yes.
more transparent in what you're writing, right? You can just kind of be upfront with the reader and say, oh, these two resources interact in a weird way that no one has been able to separate all that well. And you have these results we talk about, if you don't have enough magic, and these other results if you don't have enough entanglement, and some results which mix the two. And here we're going to try to investigate these two regimes. And that's enough. Right? You don't need to then try to kind of pin that on saying, no, now I did an MPS thing, but now I'm looking at universal quantum computation, which, like you were also looking at that before. So that was the criticism, right? More in terms of like how you write the motivation rather than the work itself, right? As I said, like I like the work. The work itself is very good. I just thinking, like if a student is reading this, a future student is reading this text as a way to learn about this stuff, like writing the motivation in this way might kind of propagate a little bit this confusion, I think.
Okay.
There's another thing that I wanted to ask is, so, in these, like, you defined two different ensembles of quantum circuits, right? One is the MBS one, where you chose the weights like a Gaussian distribution or something. And for the Clifford ones, you just constructed a random Clifford and then just added the T-gates randomly. Do you have a good justification for those specific ensembles?
No.
Okay.
The idea of use random something is that we know that random something in general concentrates near random states have high entanglement. We know that.
Mhm.
And so in MPS, this is good because we wanted to saturate entanglement. And in Clifford, it is also good because, as I discussed, as I tried to do, the idea was to saturate entanglement too. So this was the only idea. The one property that I thought about was the saturation of entanglement. And because of that, I used these two ensembles. For the MPS, it's just some naive way. This is even not the right way to generate higher states. You have to do something more complicated.
Right.
But this is already sufficient to saturate entanglement.
Sure.
I mean, under the bond dimension restriction. And for Clifford, it was just, I mean, my idea was a little naive. I thought that maybe if I just scramble circuits and put them randomly, I will get some hard-like circuit. I thought about that. And so I didn't, I admit that I didn't thought about how this ensemble generating way would affect the results.
Okay. Yeah, because I mean, I think that's worthwhile discussing a little bit more in detail. Because again, like if you have like the Haar ensemble, right, that has a bunch of nice symmetry properties that you understand. But if these ensembles are just kind of, I think there's a perfect valid way of just building a random circuit. But if they don't have well understood properties, then I think you might want to be careful about your conclusions, whether your conclusions are robust to changing this ensemble a little bit, right? So as we were talking before, like if you have this kind of very deep Clifford circuit and you just kind of splatter the T-gates anywhere, like, is that the best way to get high complexity? I don't know, maybe it's not, right? So, if you think about magic circuit injection, for example, you can get like arbitrarily complex states just by having all your T-gates at the very first layer if you want. And that's already very hard, right? Because you can just kind of inject the T-gates in the middle. So I think it would then be good to try maybe a few different ways of doing these ensembles just to see if the outcomes are robust, right? Because if you find out, if my T-gates are much closer together, then all that complexity vanishes, for example, right? And then you say, well, maybe the conclusions are maybe less robust to this choice than I thought. So I think, this is worthwhile spelling out in the dissertation and kind of telling the reader that you made this particular choice, not with any previous motivation, just as a, one way to choose that, it's okay. But then, that it's a good open question whether the results are robust to having made a different choice. I think it's worth it. And one thing, like if you look at the probability distribution graphs for the two ensembles, right? If you look at the one that has like very high bond dimension for the MPS and the other one that has very high number of T gates, they start to kind of look the same,
Yes.
right? The ones with very small, very kind of small bond dimension or very small number of T gates, they look very different. But then they start looking the same, and that's a good sign, right? That says that you are reaching some common limit in both regimes. So that's, I think, that's also a thing that's worth investigating, right? Are these two, they kind of visually look the same, but are they similar? Like how would I check whether these distributions are close to each other? I feel like plotting them in this kind of ordered way where you just had these bunch of noisy looking things, maybe, I don't know if that's the best way to plotting it. I would maybe like sort the probabilities so you can kind of, yeah. But then if you sort the probabilities and they look almost exactly the same, right? Then you can say, yes, both of these ensembles have converged to something that's similar. So then, that suggests that the conclusions are actually robust. So I would suggest kind of looking a little bit at that.
You can even try to quantify that via some K-head divergences or something like that. So you can even, let's say, try to make it quantitative, this comparison.
Yeah.
Okay.
Yeah, I think that's worthwhile doing.
I think that even Fernando talked about that because technically, if we have MPS, I don't remember anymore, but as you said, if MPS with high bond dimension should be similar to Clifford circuits with a lot of G gates, and it's weird because we didn't get the same results, and we need to thought a little more about that. Why we didn't get the same results.
Yeah, exactly. I was even about to ask maybe if any of you know whether like the bond dimension. So if I have just a Clifford circuit without T gates, if there is like an upper bound on the bond dimension or something like that. I mean, the kind of entanglement that you get is probably not very hard kind of entanglement, right? So it maybe the bond dimension will be not that high, I'd guess, but I'm not sure about. Would you know that? Daniel or
I
Dario, or
don't
maybe
know.
João? Because these would maybe correlate to
Yeah,
results,
but I mean,
right?
you can get very high, like, I mean, you would get probably very high, like Schmidt ranks around like through every bipartition, right? So
With Clifford gates without T gates,
without
I mean,
T, yeah,
yeah.
right? Probably, I guess.
I'm not sure. I mean, yeah,
You can
probably.
get like very graph states that are very
Sure, yeah, that's true. Yeah.
entangled across every bipartition.
Yeah, definitely. Yeah.
But
Yeah, you can just
which
kind of
doesn't mean that there's a kind of a different basis you can rotate or whatever that you can do that's gonna give
sure,
a
yeah.
better MPS simulation of that, for example.
Uh-huh.
But I would expect like a straightforward MPS description
Only.
of this would just have high bond dimension because
Yeah, you're right. You're right. Yeah, sure. Thanks.
Okay, so I think those were the most important things I wanted to discuss. I mean, the thing with the ordering of the probabilities in the plot, right? Plotting them sorted rather than just is that if you look at the for instance, the first row of the just Clifford ones, which has like a brick of red, but a bunch of the probabilities are actually zero, but you don't see that because there's 1,000 and they're kind of all mushed together, right? So if you sort it, now you know exactly which fraction of them are zero and which fraction are non-zero, right? So I think that's kind of a better way to represent maybe this data, because the labels of the outputs don't matter anyway, right? Like all of these ensembles are permutation invariant, I think, right? Well, maybe
Yes.
I don't know if the MPS ones are, because there's kind of, you have like these boundary conditions, right? But the Clifford one's definitely permutation invariant.
No, as you now talked, MPS I agree, but Clifford I generate it in some way that's local.
No, sure,
If I
but
remember well.
if it's long enough, right? So if it's deep enough,
Yep.
that should vanish, right?
Okay.
And for all the plots, for all the plots of Clifford plus T, you are taking very deep Clifford circuits anyway, right? So you wouldn't expect that, like you wouldn't expect some of the I mean that was a question that I have, right? So you always do nearest neighbor Clifford gates, right? Is that true? That feels
Yes, I
true
do.
from the figure,
Yes.
yeah. I mean, but again, since swap is Clifford's, that shouldn't matter if it's deep enough, that should stop matter, I guess. Yeah, so but in any case, since it should be kind of morally permutation invariant, I think the ordering of the output doesn't matter anyway, so we could just kind of sort the probabilities. Let's see. I think let's see if I have any other relevant comments here. Oh yeah, one which I think you did kind of mention, but when and this is related, I guess, to all of these questions, right? So the behavior, like the learning behavior, changes when you start adding the T gates. How do you know that that's not just from like the distribution not being so sparse now, right? So how like because the distribution, you start getting more different values of the probability distribution. Like it's completely different thing from the MPS side, right? On the Clifford plus T, the distribution starts looking very different because now you get a bunch of different values for the probabilities. If you have, just Clifford, it's always the same values. But if you have T, the more T gates you add, the more different values you get for the probabilities. Like that's you can see that from the plots. And also the distribution gets less sparse. So how do you know that, those are not more important factors for the learning compared to just like, computational complexity?
You said about the difference between the dense distribution with high number of T gates and some sparse distribution in the beginning.
No, yeah, I just mean like, when T equals 0, right, the distribution is very sparse and only
Yes.
has a few different values of the probabilities. So you would assume that's very easy to learn independent of its computational power, just from being like a very kind of uniform like looking thing. But the more T gates you add, it becomes less sparse and you get more different values of the probabilities. That's very different from what happens with MPS, right? With MPS, none of these things happened right from the beginning, but with Clifford they do. So I guess my question is, how do you know that, the sort of consequences for the learning part aren't just from the probability distribution becoming less sparse, for example, compared to any kind of computational complexity? Do you know, like,
I think that
yeah,
first, I don't know. I didn't ask this question. But if we can compare, for example, with the results from the MPS,
right.
because as you said, it's always somewhat densely distributed. And we see that even if you have the same dense look distribution, we have this kind of positive trend. We have this increased trend. And so what I want to say is that maybe it's not just due to that, because if it were, we would see the same kind of plateau with the MPS results, within the MPS results, but we don't see that. But I agree that this is not like a general argument. I need to think about more. Simply don't know if it's due to the difference in sparsity. Maybe it can be.
Right, because for the MPS, maybe it's kind of easier because the thing that the kind of neural network is learning is this sort of low entanglement fraction of Hilbert space or whatever, right? If you like the one dimension is small. But for Clifford, the thing that makes it classically simulatable is this kind of algebraic structure of the stabilizer theory, right? So it's the fact that you can kind of represent it as these kind of transformations, these kind of affine transformations in a much smaller dimensional subspace. But maybe the machine is not seeing that because maybe that's not obvious from the output distribution. The thing that is more obvious from the output distribution is the sparsity. And then maybe that's kind of it's changing what happens in the end. I know. I'm just kind of speculating, but I feel like, the Clifford has this thing. Maybe it's what you mentioned, like the example you were doing with the modular arithmetic, right? Maybe, like if you added enough examples to it, then maybe it would learn the underlying kind of algebraic symplectic structure of Clifford's of stabilizer theory, right? I know.
Yes.
I'm speculating. That's maybe a worthwhile thing to think about. Yeah, okay. So yeah, I mean, those are the comments that I had. I have a few other kind of minor comments, but I can just send you the PDF later. But yeah, once more, like, congrats. I think this was very nice work.
Thank you.
Thanks a lot, Daniel, for nice comments. And I mean, we are waiting to have your annotated PDF in order to improve the dissertation. Dario, if you also have a annotated PDF, please send to João or to me. I'll be happy to pass to him. Okay, so we don't have questions from the YouTube. So people from YouTube, if you have questions, now is the time. And meanwhile, since there's a delay, so we have to wait a little bit if they write something. How do you want to make any comments? Do you want to make questions?
Mute. Okay. No, no.
Okay, well, that gave people in the YouTube, I mean, enough time, so they didn't write anything. Dario, do you want to start again? Do you have more comments,
No,
questions? Do you want? No, it's okay.
no, I think is, I mean, I share with Daniel that there is that, I mean, the work is really good, especially for a master thesis. I mean, so yeah, it's very good.
Exactly.
Yeah.
All right, so then, I don't know, Larissa, so I'll switch to Portuguese. Larissa, eu não sei como a gente faz agora
Oi,
para
Fernando.
fazer a... Oi, Larissa. Bom, aliás, agradecer também a Larissa e o pessoal da Coedu por, né, arranjar aí, não só conseguir um horário com todo mundo, mas também por botar aí o Zoom e coordenar isso. Muito obrigado.
Nada, que isso. Agora eu vou enviar o pessoal da banca para uma sala simultânea, onde vocês vão deliberar, tá? Aí, assim que vocês
Beleza.
terminarem, vocês retornam para essa mesma sala. E
Tá
eu e o
ótimo.
João ficaremos aqui aguardando nessa sala aqui, tá bom?
Tá bom. Muito
É só
obrigado.
aceitar na tela de vocês, por gentileza.
Tá.
Ok.
Estamos de volta. Estamos de volta, Larissa? Tudo certo?
Tudo certo.
Tá. Bom, João, a banca deliberou, mas você sabe, como de costume, antes de dar o resultado, eu gosto de falar algumas coisas, né? E eu vou tomar liberdade, Dário, de falar essa parte em português, se você não se incomodar.
Sim, você pode, eu vou entender bem.
Claro,
Vocês
obrigado.
conseguem me ouvir?
Sim.
Sim.
Bom, João, assim, eu queria, né, te agradecer por esses já 3 anos, né, de trabalho. E eu estava até comentando com o pessoal da banca, né, que você é certamente um dos alunos mais brilhantes com quem eu já tive contato, né? E como eu comentei com eles também, isso vem como um- uma coisa boa, mas também talvez um peso, né? Então, acho que você recebeu um problema que não era tão bem colocado, né? Assim, estava mal colocado, vamos ser bastante claros, né? E você percebeu o furo, né? E corrigiu, né? Você achou o problema, né? E isso é muito distinto do que é esperado de um aluno de mestrado, né? Então, realmente você superou em muito assim o que era esperado de um aluno de mestrado. E no lado que isso é um problema é que acho que por um lado você ficou relativamente sozinho, né, durante o seu mestrado, né? Acho que vocês a banca e você sabem muito mais do que Raul e eu, né? Então acho que você tomou o caminho e foi sozinho. A gente meio que acompanha, tentando
Fui guiado.
minimamente te orientar, mas orientar você é só tipo te trazer para o problema, né? Não deixar você é, divergir, né? Então é muito fácil e um grande prazer trabalhar com você, apesar de eu ter assim que talvez pedir um pouco de desculpa de você ter ficado talvez assim tão sozinho, né? Bom, dito isso, não sei se Raul, você quer falar alguma coisa?
Só quería agradecer por el tiempo que colaboramos y pasamos juntos. Y parabéns y te
É,
deseo
Obrigado.
un excelente futuro.
Obrigado.
exato.
A
Então,
gente ainda vai
calma aí,
colaborar um
rapaz,
pouco
ainda não
mais.
dei o resultado, não. Não sabe o resultado
Desculpa.
ainda. Bom, dito isso, né, claro que a banca te aprovou por unanimidade, então parabéns, mestre João Pedro.
Obrigado.
Parabéns demais, viu? Eu também vou dar aqui os claps,
Parabéns, João.
se eu conseguir.
Bom, eu posso
Parabéns,
falar?
João. Pode falar, fique à vontade. O microfone é
Eu
seu.
queria, bom, agradecer a banca por ter aceitado. Eu gostei. Eu estava esperando bastante as opiniões de vocês para saber como estava. Eu gostei muito, né, de ambas. Elas meio que tocaram bastante na parte da especialidade de cada um. Eu gostei disso. Pelo tempo. E também agradecer Fernando e Raul por esses 3 anos, como eles falaram. Eles me ajudaram muito. Embora eles estão falando isso, é, foi, foi muito legal trabalhar com eles, a ajuda deles, as aulas, os puxões de orelha e tudo mais. E, claro, quem está assistindo isso. Eu não sei se isso está no YouTube, mas obrigado
Tá
também.
tudo no YouTube.
Vixe?
Tivemos um pico de, sei lá, 13, 14 pessoas assistindo, agora são tão 7, porque as perguntas é um pouco mais árido, né? Mas, bom, então é isso. Parabéns, João Pedro. Obrigado,
Obrigado.
Dari e Daniel.
Parabéns, João.
Eu-
Obrigado, gente, pelo
Bem,
convite.
Obrigado, Dario y Daniel también.
obrigado.
Obrigado
Parabéns,
a
João.
Larissa.
A
Isso, obrigado,
Larissa.
Eu que
Larissa.
Obrigado.
agradeço, gente.
Tchau, tchau.
Tchau.